The first popular synthesizer was the analog Moog synth created in 1964. In 1987, the Yamaha DX7 was released, popularizing the digital synthesizer. Both analog and digital synths have been used extensively in music, but they produce their sounds in different ways. While analog synths operate exclusively through analog circuitry, digital synthesizers manipulate the notes digitally in an attempt to recreate the sound of analog synths. Currently on the internet, there are many do-it-yourself synthesizer circuits, but there is little guidance for self-design. Our goal is to provide a more focused analysis of synths than what can be found online. Our project provides insight such that musicians and tinkerers can have a more concrete basis for creating their own synth.
One of our main constraints was the budget. Because our goal was to build affordable DIY synths, we limited how much we spent. We were also constrained by the functionality of the Arduino language, through which we built our digital synthesizer, as well as the use of common circuit components for the design and construction of our analog synthesizer.
Some notable standards that we used were the standard tuning frequency, which we used to tune each of our notes from C4 to C6, as well as the standards defining the coding language C that Arduino uses. We also used the restriction of hazardous substances standard for safety in choosing electrical components.
We decided to start with the analog synthesizer, which has three main components: the voltage-controlled oscillator, or VCO, the low-frequency oscillator, or LFO, and the analog filter. The VCO is an oscillator that changes in frequency depending on the voltage input. The LFO adds tremolo to a circuit, and the filter attenuates certain frequencies, altering the sound. We created the VCO circuit as well as the LFO circuit, though they only output a square wave, and we wanted a triangle wave for the LFO and a triangle wave option for the VCO. We built a voltage divider keyboard using 5 push buttons, though we had planned to expand this to 2 octaves. We also built a negative rail generator that creates a negative output from a positive input. Due to COVID-19, we were unable to complete our analog synthesizer. This would have included the implementation of a negative 9-volt rail and triangle wave outputs, the integration of the VCO and LFO with a tuning input, and the addition of an analog filter. We then would have constructed a full keyboard with higher quality buttons, and built a housing and portable power supply method to turn our circuit into a finished product. This is the circuit that we designed. The keyboard consists of several buttons acting as switches that, when closed, allow power to reach the VCO, as well as powering a voltage divider to provide an input to the VCO. The VCO, built using a 555 timer, can have a frequency range of over 2 octaves. The LFO is designed using a Schmitt trigger and is controlled with a potentiometer. A tuning input was planned to integrate with the LFO into the VCO, which would have a triangle wave and square wave output. This would enter a filter to attenuate the signal. The negative rail generator, used to provide a negative voltage for the integrator and adder circuits, uses a 555 timer and clever capacitor placements to create a negative charge on the capacitor's plate.
Our digital synth consists of an Arduino and its corresponding input and output circuitry. The Arduino takes a voltage input which it converts into a frequency output, just like with the analog synthesizer. The digital synth uses a potentiometer knob to control this voltage input over an octave range, though it could also use a voltage divider keyboard. It has an additional switch that moves the output up an octave. The Arduino then adds a tremolo to the note, much like the LFO of the analog circuit. It uses potentiometer inputs to control the magnitude and frequency of the tremolo and an LED that blinks at the tremolo's frequency. The output stage begins with an RC filter using a potentiometer and capacitor to filter the sound. Due to limitations in the Arduino functions that we used, we built an analog filter instead, which also showcases the potential for our analog synth. The potentiometer controls the cutoff frequency of the filter, which softens the sound and makes it less harsh. The output of the filter then goes through an LED and a button before the speaker, so that the notes can occur separately from the frequency and have an LED turn on whenever a note is played.
While we didn't get to analyze the analog synthesizer, we were able to measure various notes of the digital synthesizer with a microphone. From these, we used MATLAB to measure the frequency and SNR of each note, as well as visualize their frequency spectra. The periodogram of C6, for example, can be shown here. The fundamental frequency was measured at 1046.88 Hz, compared to an actual frequency of 1046.5 Hz, and the overtones, which are all multiples of the fundamental frequency, are clearly visible as well. From this data, we can verify our success criteria.
Our first criterion is that both synthesizers are able to generate notes that are within 1 Hz of the intended frequency, as the average human ear can only begin to discern different notes around 3 Hz. Though we have no recorded data, the analog synthesizer was always within 1 Hz of the expected frequency, as we visualized on an oscilloscope. The digital synthesizer was on average 3 Hz off, with a maximum difference being 8 Hz off, but this could be due to the low fidelity of audio recording as opposed to directly measuring off the board with an oscilloscope. Our second benchmark was that we could make a VCO that is able to convert a voltage input between 0 and 5 volts into a frequency with a range of at least an octave, and both the analog and digital are able to do this. In addition, we wanted to make an LFO that could oscillate between 1 Hz and 10 Hz. In practice, we got our analog LFO to oscillate between 2 and 12 Hz, and our digital between 1.25 and 10 Hz. Though these are not exact, we hit the rough range of our LFOs with success. Thus, our digital synthesizer is able to replicate both the frequencies and rough LFO range of the analog synth, achieving yet another success marker. Lastly, our original goal was to build our synthesizers for less than $50. The 2 synthesizers were completed using only $19.46, in addition to free parts from the lab.